All right, so the next thing we're going to talk about are dilations. So I want you to write this in your notes. Dilations are a transformation that either stretches or compresses. And we're going to make another chart in our notes. And on one column, we're going to say what the dilation is. And in the other column, we're going to write the change to the parent graph. Okay, so dilation. All right, so I just want you to write these down for now, and then we're going to talk about them and we'll see them in examples. But if we have, let's say, f of x, and we simply just multiply the function by a value, let's just say by an a value, so a times f of x. And we're going to assume here that a is the absolute value of a, we're going to put is greater than 1. Okay, so this is the rule. I'll keep it all in blue. We're going to assume that the a value that we're multiplying by is bigger than 1. The absolute value is bigger than 1. And what does that do? That means the graph is going to be stretched vertically. So we're going to put that down. So we're going to say graph is stretched vertically. Okay. Now, if we have something where a is below 1, right? So let's say we have a times f of x, but in this case, the absolute value of a is in between 0 and 1, so it's really close to 0. It could be like negative 0.5 or positive 0.5 or what have you. Then it's going to be compressed vertically, or we can think of it as a vertical compression. So we're going to say the graph is compressed vertically. Okay, now we can kind of see that if we look at something like this, right? If I have f of x and I multiply this x squared, so let's say it's x squared, if I multiply that by an a value of 2, right, you can see that we can think of this as being stretched vertically, right? You can also think of it as a horizontal compression too. Some of these things are equivalent that we're going to talk about. But this is sort of stretching it out vertically. However, if I make the a value like 0.1, right, then you can think of it as a vertical compression. It's kind of being smashed, right? Let's start at 0.6, then 0.5. The further or the closer we get to 0, the more compressed vertically it is. And you can also think of this horizontally as a horizontal stretch even. So that's what it looks like on Desmos, right? That's a vertical compression. Now, two more that I want you to put in there. If we take, instead of a times f of x, if we take f of ax, or a times x, and again, we are assuming here that a is a positive, or a is bigger than 1. The absolute value of a is greater than 1. Then we can think of this as a horizontal compression. So we can say the graph is compressed horizontally. Now, you might, in some functions, when you have like f of ax here and ax, there's really no difference, or not much difference, between these two things here. It depends on the function, and it depends on the characteristics of that function. So Keep that in mind. All right, and then the last one we want to put is f of ax. But if the absolute value of a is in between 0 and 1, and we can think of this as a graph that is being stretched horizontally. And so we're going to say graph is stretched horizontally. Okay, so these are all of our dilation rules. So I want you to write those down because we're going to come back to them as we examine functions. As we look at them, we'll kind of refer back to these things. Now the second set of things that I want you to put down are reflections. Okay, so we have translations, which we already talked about. We have these things called dilations, which is kind of stretching the graph horizontally and vertically. And the other thing I want you to put in here in our last transformation is going to be reflections. A reflection is just a transformation where a figure, or how about we just do this, where a graph is flipped in a line of reflection. Okay, we've seen this before. We talked about reflections when we talked about like even functions. That is just a reflection over the y-axis. Okay, so we can think about these things as reflections. Now there are two types of reflections that I want you to write down. There's just an x and a y reflection. So first thing I want you to write down is negative f of x. If we ever just take the opposite, right? If we take the opposite of f of x, what is going to be the change in the graph? The change in the graph is going to be that this is a reflection in the x-axis. So we're just going to write, here's the rule for that. This is going to be a reflection in the x-axis. Right? And then the other one that we have is f of negative x. This should kind of look familiar with even and odd functions. So this is going to be a reflection in the y-axis. Okay, so those are our last two rules. We have these dilations, we have these reflections. If I were to just show you quickly on Desmos what this looks like, if we took f of x and it's x squared, and I took negative f of x, right, you can see it's a reflection over the the x-axis right here. Right? This would be the same thing as just taking an a value and just making this negative 1. Negative 1x squared is going to be a reflection over the x-axis. Now, if I did a reflection over the y-axis, it would kind of look like this. It would be f of negative x. Right? And if you look at that, it does reflect over the y-axis, but this is an even function. So therefore, it's the same graph. Right? So if I plug in negative x, another way to see that, if I said g of x and I said, well, this is going to be negative x all squared, right? Really, you can look at those exponents and say, these are really the same function, right? Technically, you can think of it as a y-axis reflection, but it's really just the same thing, because negative x squared is still x squared.